Hello everyone, my name is Ehsan Entezari. I am corresponding author of a paper as the evaluation of quenching temperature effect on microstructural and mechanical properties of advanced high strength low carbon steel after quenching partitioning treatment. This paper is going to be presented for fourth international conference on structural integrity. I am from Department of Metallurgy and Materials, Instituto Politécnico, Nacional, Mexico City, Mexico. Our presentation contains four parts: introduction, materials and methods, results and discussion, and conclusion. Introduction, Part 1. Advanced high-strength steels are widely used in automobile parts industry, especially to manufacture lightweight vehicles that have to meet high safety standards and provide better efficiency. Advanced high-strength steels are classified as quenching and partitioning, tempering, training induced plasticity, transformation induced plasticity, and dual phase. Recent studies have focused on quenching partitioning and quenching partitioning tempering heat treatments. According to Chevrolet annual reports, as you can see in this slide, more than 50% of body structure mass of automobile is produced by advanced high strength and high strength steels. Part 2, materials and methods. In this slide, you can see our methodology in producing an advanced high strength low carbon steel with considerable microstructural and mechanical properties. First of all, as a first step, the scraps were melted and remelted to produce colored ingot with low segregation. The remelting process was done by electrostatic remelting process, and in second steps, the produced ingots were rolled at 1000 degrees Celsius. In the following, the samples extracted from rolled plate were quenched and partitioned according to this schematic diagram. All samples were austenized at 900 degrees Celsius for 30 minutes, and immediately all samples were quenched at three different temperatures, and these temperatures are located in region between Martensite start and Martensite finish. These temperatures are 260 degrees Celsius, 280 degrees Celsius, and 300 degrees Celsius. And the samples were punched for 2 minutes, and also then partitioning treatment was done at temperature above Martensite start. This temperature is above 340 degrees Celsius for 4 hours, and finally all samples were cooked at water. Furthermore, microstructural and mechanical studies were done by optical microscope, scanning electron microscope, X-ray analysis, and tensile and impact testing. The aim of our paper is to identify the optimized quenching temperature with the highest mechanical properties. Part 3 Results and Discussions. Here in this slide you can see optical and scanning electron microscope micrographs of samples quenched at different temperatures. According to these micrographs, we found that decreasing in quenching temperature, the steel was quenched at 260 degrees Celsius, had a high volume fraction of tempered martensite like this and this, and high volume fraction of blacky austenite or martensite like this and these phases. This slide shows valuable information on the effect of quenching temperature on magnetic thickness, where decrease in quenching temperature from 300 degrees Celsius to 260 degrees Celsius decreased the average thickness of magnetic ferrite subunits. This effect could improve tensile and impact properties of sample quenched at 260 degrees Celsius, as you can see in these tables. That is, this sample or the sample quenched at 260 degrees Celsius had the highest tensile and impact properties. However, decrease in magnetic plate thickness has a more effect on impact properties of studied samples. This slide shows scattering electron microscope fracture photographs of tensile and impact test specimens. It can be seen that the fracture surface of tensile test specimen quenched at 260 degrees Celsius is micrograph consisted of combination of shallow and deep rupture dimples like these characteristics, whereas Charpy impact test specimen showed combination of cleavage faces like these characteristics and shallow ductile rupture dimples like this figure. Noted that the ductile fracture dimples, as you can see in this figure, like figure number A and D, are formed in the retained austenite regions, and the cleavage component of fracture, as you can see in these figures, the cleavage components, as you can see in this figure, are formed in low ductility constituents like the region with martensite and bainite phases. This figure in this slide shows the XRD spectra of studied samples. The volume fracture of returned austenite for samples quenched at 260, 280, and 300 degrees Celsius was 12, 14, and 70% respectively, An increase in quenching temperature raised the amount of residual austenite and increasing the volume fraction of residual austenite can enhance the toughness of quench partitioning treated specimens by increasing the ductility at the crack tip, but it may not be the only reason because in this study, fracture toughness increased with decreases in volume fraction of retained austenite. Thus, bionetic sheets with various crystallographic orientation may be a contributing factor to further increase the toughness of the test specimen quench at 260 degrees Celsius. Conclusion: the quench partitioning treatment of advanced high-strength low carbon steel can produce a good combination of strength and ductility and decrease the fracture toughness by decreasing the quenching temperature. It was observed that increasing quenching temperature from 300 to 160 degrees Celsius increased the volume fracture of martensite microflux and reduced thickness of bionetic plate. Low quenching temperature also reduced residual austenite and produced finer bionetic plates with various crystallographic orientations as well as higher volume fraction of martensite microflux and tempered martensite. These microstructural characteristics enhance the mechanical properties by hard-phase mixture and fine size of second phase strengthening mechanism. Thank you for your attention.